Dear students, welcome to the sixth week of the offshore production engineering. So before the midterm, 2 weeks, we have approximately 1 or 2 weeks to the midterm. So we will today discuss about the buoyancy and stability issues which faced in the offshore environment in the platforms, and we will talk about the physics behind that and how it's happening, and some calculations will be included as well. So Week 6, buoyancy and stability, and continue. All right, let's start it. So buoyancy and stability. So any seaworthy vessel must obey all the laws of hydrodynamics for the safe operation of drilling and the production, as well as during movement from one location to the other. Okay. So thus buoyancy and gravity become two very important factors which play a big role in determining the stability of any floating unit, right? So buoyancy is the apparent loss of the weight of a body immersed in a fluid. So it was a Greek scientist Archimedes. We all familiar with this name, you know. He lived in the years of 287 to 212 before Christ. So he discovered that the weight of a body floating in a fluid equals to the weight of the volume and the fluid displaced by the body. All right. So in precise terms, the Archimedes principle is stated as follows. All right, as follows. A solid body, wholly or partially submerged in a fluid, is buoyed up by a force called mb times g, equal to the weight rho w times v of the fluid displaced. Okay, so it's a kind of relation between the mass and its volume, right? And the density is another parameter, and the gravity is another parameter that affects the function of this, right? Okay, let's talk a little bit about the theory and the analysis, okay? So referring to the figure, the MB is the mass of the fluid displaced by a ship of mass in air equal to MO, okay? MO. So V is the volume of the water of constant density, rho W, all right, rho W, displaced by the ship of weight in the air, MOG, okay, in the air part, the MOG, right? Thus, the upward pressure of the displaced water, called that is buoyant force, called mb times g equals to rho w times v, the volume, all right? So in naval terminology, v times rho w, that is the weight of the volume of the water below the water line, which is occupied by water, is known. This is known as displacement. Displacement, all right. So it is to be noted that dimensionally, this is not the length, but it is weight. So we are not talking about the length in here. We are just talking about the weights in here, all right. So now the above buoyant force called mbg, okay, as you can see, the above buoyant force acts as a point B known as the center of buoyancy, all right. So center of buoyancy of the ship in a vertical direction, opposite to that the gravitational force itself. Gravitational force MOG, right? So which acts as a point of G, all right, in here known as the center of gravity. As a force of buoyancy is vertical force and is equal to the weight of the fully displaced fluid by the body, the center of the buoyancy will be the center of the gravity of the displaced fluid of constant density in here. Okay, this is a generic instruction for a partially submerged ship in the water, right? Seawater, let's say. So this is the main mechanism, physical mechanism working in terms of the buoyancy. We already familiar all of these, all right? But just I would like to give as a generic information, right? So assuming a ship or rectangular shape of length L, height h, and width beam b, and the material density, all right, rho, partially submerged in a water of density rho w, as you can see in the figure, up to a height called d, all right? So known as the draft we are talking here. From the bottom of the vessel, the height of the center of buoyancy can be found as what? For the equilibrium buoyancy force, mbg equals to gravity force MOG, or the weight of water displaced equals to weight of the ship, or L times P times D times rho W equals to LBH rho, right? Here we can reach to the formula that called as D equals to H times rho divided by the rho W, right? Rho divided by the rho W, right? Okay, so hence the height of the center of buoyancy, the formula becomes like this according to the structure, the gravity platform we are talking. Here, let's talk about the gravity platforms. So here, of course, it's in the upright position partially. So here, the formula HB equals to D divided by 2 equals to H divided by 2 times rho divided by rho W. So in case of a two-liquid system for an arbitrarily shaped body, the location of B can be found out in a similar way. Consider the gravity platform partially submerged in the soft mud as shown in the figure. All right. According to this, so you have to consider the gravity and the density and the volume of the mud itself as well. So the same thing can be done in here, and according to formula changes according to that. All right. So the different types can be applied, all right, for different types of structures. So here we assume that the water saturated mud level behaves as a liquid whose density is rho m and the volume of displaced mud Bm. All right. So the buoyant force at the center of the displaced mud or sand volume is equal to rho m times Bm. Definitely. The portion of the caisson's volume above the mud line called Pc. Buoyant force for the portion of the caisson, all right, called rho W times Vc. Okay. And submerged volume of each leg called V1. All right, V1. So the total number of identical legs are n. Let's say n to this. How many legs it has according to here it's 2, for example. All right. So buoyant force of each leg on each leg called rho W times V1. Total buoyant force on the legs are n times rho W times V1. And the summation of these buoyant forces, rho m times Vm plus rho water times Vc plus n times rho W and V1 equals to mb times g. Okay, so you have to equalize the equation according to the weight, change of weight, volume, and the density, of course. So according to that, in the light of all these ideas, this total force will be acting through the center of buoyancy of the whole submerged structure. So if the height of the center of buoyancy equals to hp, then equalizing the total moment with the sum of individual moments, we get this formula. Okay, this formula. It's the total. All right, calculation total. Thus, what happens? The height of the center of the buoyancy for an upright position of any structure is calculated. Once again, referring to this figure, if a vessel is floating with some portion, let's say, let's not refer to this one, the previous one, the rectangular one, let's refer to, all right, remember the rectangular one, okay? So refer to that figure. Let's say if a vessel is floating with some portion of its watertight hull still above this water surface, it has reserve buoyancy, right? So that is, if additional weight was added to the vessel, it would still float, and the total weight that would have to be added to cause it to sink is called reserve buoyancy. Okay, so the word reserve in here means standby, right? Which is required for withstanding forces of mind. Okay, the forces of wave, the wind, current, accidental flooding or shifting of the weight aboard the unit. All right, is all affected. So thus the reserve buoyancy is defined as the buoyancy above the water line. What is the reserve buoyancy? It is let me continue, let me repeat it again. It means the standby required for the withstanding forces of wave, wind, current, accidental flooding, or shifting or weight aboard the unit. Okay, so thus what we can say, if we say the reservoir buoyancy, it is defined as the buoyancy above the water line. For example, the volume of the unit from the water line up to the freeboard deck that keeps a vessel upright or seaworthy when subjected to wind, waves, currents, and other forces of nature, or to accidental flooding. Okay. Another one is a freeboard. We call freeboard is the vertical distance between the water line and the uppermost continuous deck, which is not watertight, and this position of the deck is known as the freeboard deck. Okay, starting from the surface of the water through to the upper part of the continuous deck, right? Okay. All right. So another one, we will talk about stability. Stability of a floating vessel is defined as the ability to remain upright or return to an upright position when subjected to the forces of nature. For example, because of wind, because of waves, etc. So the operation itself, it can be resolved by the operation, by accidental flooding, etc. Right? So in other words, we can say to define simply, the stability is nothing but the resistance of a vessel to capsizing. Okay. So as mentioned previously, the criteria for the stability revolves around two different terms: the buoyancy and the gravity. Right. Also a very important parameter that relates to these two terms is they call it metacenter. Metacenter. All right. So it is the metacentric height, which is considered to be the adequate criterion for the stability. Metacenter. All right. So here, two different figures we are seeing in figure N and B. All right. So here we also mentioned the semi-submersible and the drill ship are shown in the upright position, where the center of gravity G and the center of the buoyancy B lie in the same vertical plane, and also in the second part we can say in tilted or rolling position being inclined by an angle of heel called theta. Okay, it's called theta, right? So when the center of the buoyancy B moves to a knee position B, let's say B times, okay, B up, all right. So it is to be noted that when a vessel is rolling by some angle, this is known as the angle of the heel, and when a vessel is pitching by some angle, this is known as the angle of trim. Okay, angle of trim, angle of the heel, angle of the trim. Okay, so for all particular or for purposes, stability against capsizing refers to the healing. Okay, any type of healing I am talking about, right? Okay, so as shown in figure A and B, when the floater is given a small angular displacement called heel, okay, the displacement in the clockwise direction, the line of the action of the force of buoyancy in this knee position called B1 will intersect the normal axis of the unit at some point of M. This point M is called the metacenter. All right. Okay, so here, how we can say this one? In other words, we can say the metacenter may be defined as the point. Okay, this is the metacenter point. Defined as a point at which the line of action of the force of buoyancy, okay, will meet the normal axis of the floater when it is given a small angular displacement. Okay, so distance, the gm, let's say distance g times m, that is the distance between the center of gravity and the distance between the g and m gives the distance between the center of gravity and the metacenter of a floating body, and it's called metacentric height. And the distance bm, let's call about b and m, okay, that's the distance between the center of buoyancy and the metacenter of the floating body. So it's called metacentric radius. Metacentric radius. Okay? Between G and M, if it is between G and M, G and M, okay, G and M, all right? So we call it directly the metacentric height. And if it is between B and M, the buoyancy and the metacenter, called metacentric radius. Metacentric radius, okay? Okay, let's go. Referring to the figure in A and B, relationship between the metacentric height and the metacentric radius can be established as follows. Gm equals to Bm times Kb minus Kg. The point K known as a keel indicates the bottom of the unit. Bottom of the unit, keel, all right? Heel and keel, don't forget this, all right? It's bottom of the unit. Okay, so here, metacentric radius determination figure, as you can see here, as a generic term of a figure. In the figure, as the unit rolls through an angle theta, a wedge of the hull on one side becomes exposed and the equal wedge is immersed. The wedges are equal because the weight of the unit does not change. So these two equal wedges form a moment. One wedge is immersed and picks up the force of buoyancy. So the other wedge is no longer immersed, gain weight since it has lost its buoyancy. Okay. So here as we come, F equals to B divided by 2. All right, B divided by 2 times 1 in here and 0.5 times W here equals to B square 1 W divided by 8 and tangent theta. Taking moments about the point B and using components of the weight F, B plus the displacement here comes as F times cos theta, B divided by 3 times 2 equals to B square LW divided by 8 and tangent theta, cos theta, 2B divided by 3, B times 3 LW divided by 12 tangent theta and cos theta. So but when it comes to the last form of that, B and B plus displacement comes to B triple times and L and W and divided by the 12 sinus of theta divided by the cos theta means tangent, and the cos theta times equals to, and I am coming to the last point, so B and B plus displacement, let's say B times 3 L W divided by 12 and sinus theta. So this is the generic formula that you will use in that, all right, for the displacement calculation. Okay. All right, let's go. But B times B plus equals to Bm times sinus theta. We already know, and the displacement equals to volume for the weight. Okay, volume and weight. Okay, in terms of weight. So therefore, Bm times sinus theta and the volume W equals to B times 3 LW divided by 12 and sinus theta we already know. And when I calculate from this one, Bm equals to 1 I divided by volume. All right, you call it in the end. All right, the L divided by volume, B3 L times B divided by 12 and volume. We call this one as I, and I divided by V we say. All right. So, for example, let's say this box-shaped unit, the moment of inertia, let's describe more. I equals to B3 times L divided by 12, and the submerged volume V equals to L times B times D. All right. So where L is the length, B is the beam, and the D is the draft of a box-shaped vessel. All right. So in general, for any shape of the vessel is metacentric radius Bm equals to the moment of the inertia, we call it I, moment of inertia we call it F, or the water plane area divided by the underwater volume, so V. So it's to be noted that the moment of inertia is a function of the beam cubed, and the slight reduction in the beam drastically affects the metacentric radius and thus the metacentric height. All right. So naval architects check drilling units as various drafts to make sure the metacentric height remains positive and sufficiently great to the unit to be seaworthy. Right. Okay. So this was the end of the week 6. So see you next week. Take care of yourself.